Recording in progress.
Hello, everybody. Welcome back to our next video in our lecture series discussing solubility equilibrium. So in our last video, we left off with this idea of an equilibrium constant that we call the solubility product, KSP, as being a constant that describes the degree of dissociation of some solid ionic compound into its respective ions in a saturated solution or in a dissociation equilibrium. And from that, we arrived at this kind of idea that there's a relationship to the amount of ions that we have in this saturated solution and what that means about the solubility of the solid in the first place, meaning how much of that solid we could dissolve. So we actually have a name for solubility. We call it the molar solubility, S, and this is something that we can quantify because the molar solubility S of a substance is the maximum number of moles of solid that are dissolvable per liter solution. This is why we call it the molar solubility, because it has units of moles of solid that could be dissolved per liter. So it looks like a molarity, but we're talking about the solid that could be dissolved up to its particular like saturation point. Saturation occurs when we hit our solubility. So as I mentioned earlier, the idea of like this measure of our maximum amount of solid that is dissolvable is something that relates to the ionic equilibrium of like the actual ions that are dissolved in the saturated solution. So let's make that statement and then prove it to ourselves looking at our crystal A2B3 again. So I'm going to say that S relates stoichiometrically to the concentration of ions in our saturated solution. Now, I know that this phrase might sound more complex than it actually is, so let's maybe translate what this means. The molar solubility of a solid is related to how many ions that solid could become ionized, right? Like how many ions are actually put into solution at the point of saturation. So let's look at this example of A2B3. So here I've got my solid crystal of my salt A2B3. And I could use this idea of solubility S to identify moles of the solid dissolvable in 1 liter of solution. So let's think about what happens when I actually do achieve dissolution or dissociation in a saturated solution. So I'm going to look at the dissociation equilibrium of this solid into its respective ions. So again, we are looking at an equilibrium occurring at the point of saturation. And what am I going to make when 1 mole of this, 1 molecule of this? So here we have 1 mole that dissociates in solution. So when I take this singular unit of crystal here, A2B3, and I dissociate it in solution, I create two A plus ions and three, let's see here, these are A3 plus, there we go, and three B2 minus ions in solution. All right, so let's write that here. So if I have 1 mole of my crystal that dissolves, then that means that I have now 2 moles of my cation and 3 moles of my anion. Meaning that this relationship can be one that is described as like for every 1 mole of solid, I generate 2 moles of my cation, and or for every 1 mole of solid, I generate 3 moles of my anion. So if I want to relate this back to the idea of solubility, meaning like how many moles of solid can I dissolve in my saturated solution in the first place, what this means is I can look at the actual amount of ions that are in solution and work backwards and say, okay, well, if I had 2 moles of this, that meant that 1 mole of solid was dissolved. Or if I had 3 moles of this ion, that meant that 1 mole of solid was dissolved. So I can use the stoichiometric relationship between these 2 ion quantities to work backward and figure out what that meant about the original amount of moles of solid that had to have been dissolved. In other words, this like phantom X that we know is happening, like we know there's some change from like no solid being dissolved to there being some solid being dissolved, translated here as our ions that are dissolved. But we're not including this like X in our equilibrium expression because again, this is a solid. So the only means we have of relating our like solubility of the solid to something that's actually in solution is by looking at the equilibrium of the ions that are in solution, because these are things whose quantities we can count and then relate via stoichiometry back to the solid. So let's maybe do an example where we look at the relationship between equilibrium and molar solubility and like the stoichiometry between your solid and your ions in like an actual example. Like, so let's leave this general A2B3 crystal and look at something a little bit, like more realistic. Let's look at an actual crystal. So practice relating the equilibrium constant or our solubility product for an ion dissociating and molar solubility S. So let's see here. I have given the KSP for calcium fluoride is this number. So I'm just going to write KSP, calcium fluoride. Calcium is in the second group of the periodic table. Fluoride is a halogen, so this means CaF2. And this is 3.9 times 10 to the negative 11 at standard conditions, meaning at some like normal set temperature and pressure, 1 bar and 25 degrees Kelvin. No, sorry, 25 degrees atmosphere, 298 Kelvin. Degrees Celsius. We got it. 25 degrees C, 1 bar of pressure. So first and foremost, part A, what is this asking? Write the ion dissociation equilibrium for the salt in a saturated solution. Okay, Lots of words here. So let's find the ones that are conveying like a very particular meaning. First and foremost, a saturated solution. This is describing a state of equilibrium between our solid and aqueous phases, meaning the solid crystal and the resulting ions that the crystal dissolved into in solution. So this equilibrium is only established when we're talking about saturation. So write that equilibrium, meaning write this equation that shows like when you have your solid, what does it dissociate into? What ions does it make? And then let's from there make a statement about the stoichiometry, meaning what are the mole ratios between our solid and the respective ions that it dissolves into to make a solution. So I'm going to write my ion dissociation equation for a saturated solution of calcium fluoride that is undergoing a constant exchange of dissolution and reassociation in a saturated solution. Then I'm going to have Ca2 plus dissolved. So that is calcium ion, and then also fluoride ion dissolved. And if I'm going to follow the law of conservation of matter, I need to ensure that I have 2 of my fluoride ions. And if I'm going to comment on the stoichiometry, let's go ahead and make a relationship here. So 1 mole of calcium fluoride solid generates 1 mole of calcium ion, and 1 mole of calcium fluoride solid generates 2 moles of fluoride ion. So the ion dissociation equation is like this, just like we would write maybe an acid dissociation equation, but here we're just looking at the solid splitting up. And then the stoichiometry commentary is looking at the mole ratios and relationships between the quantities of the aqueous to the quantity of the solid. All right. So B, at saturation, what could be said about the molar solubility of the solid and its respective ions? Meaning, how do we relate these? So this is where we're practicing what we talked about in our last slide. So I'm trying to figure out exactly how does S relate to our concentration of ions? So remind yourself, the molar solubility, S, is the maximum number of moles of solid that are dissolvable in 1 liter of solution. So I need to make a statement about the relationship between if I've put some number of moles of solid in water, then I should see these relative mole amounts of ions present in solution. So let's rewrite this. If S moles dissolved per liter then we know that the concentration of the calcium ion has to be equal to the moles of the solid, because that dissolution equation has a 1-to-1 stoichiometric ratio between the solid and the calcium ion. So if S moles of solid are dissolved per liter, then the concentration of calcium ions that we see has to be equal to that same number of moles. So we're saying calcium ion concentration is equal to the number of solid moles dissolved per liter. And let's use our stoichiometry for the fluoride to make a similar statement. Because our solid generates twice the amount of fluoride, we know that then the ratio of fluoride to solid being 2:1 means that we have twice as much fluorine as we do the solid. So all of that fluorine is representative of like twice the initial concentration or amount in moles of calcium fluoride that was dissolved. So the concentration of fluoride is equal to twice that maximum amount of solid. So fluoride ion concentration is equal to 2 times the amount of solid moles that are dissolved per liter. So if we're thinking about being at this equilibrium, right, being at saturation, then I am making a statement that relates the molar solubility, or the number of moles of solid dissolved per liter, to what that means about the number of ions, or the moles of ions found per liter, which we express as a molarity. So the concentration of the calcium is equal to the moles per liter of the solid dissolved. And the concentration of fluoride is twice as much, because the ratio of solid crystal to fluoride ion is 1:2. So what could be said about their relationship? This is what could be said. So these innately relate to S via their stoichiometry. Okay. Still haven't found a need for KSP yet, so let's keep going through this problem. So part C, what is the molar solubility S of calcium fluoride? So I'm going to rewrite some of the information that I had from the prior page. CaF2 solid in a dissociation equilibrium because it's in a saturated solution that contains dissolved calcium ions and dissolved fluoride ions in a 1:1 and 2:1 ratio, respectively. And we have our KSP value for this equilibrium, this dissociation equilibrium, being equal to 3.9 times 10 to the negative 11. And if I want to think about the initial change equilibrium, knowing that I can't think about like the solid, I know that this is going to increase from no ions in solution before dissociation to some amount of ions in solution, X, and some amount of fluoride ions in solution, 2X, where the understanding is that this X is the decrease in the amount of the solid, meaning it's the number of moles of solid that were dissolved. So I'm actually going to replace that variable with the variable for molar solubility. That is the mathematical meaning in this context of what X is. So that means then at equilibrium, I have an equilibrium concentration of calcium ion equal to S, and an equilibrium concentration of fluoride ion equal to 2S. All right. What am I being asked to find here? I am being asked to find the molar solubility. So I want to know what the value of S is. So I'm doing a normal, regular equilibrium calculation, right? Utilizing my equilibrium constant to figure out concentrations at equilibrium. But now the equilibrium constant has a new name, KSP. And this amount X, or quantity at equilibrium, has been related to the quantity of the solid that dissolved in the first place, which is why we're replacing the X with S, the solubility of the solid crystal. So equilibrium constants, these are products over reactants, where products are raised to their coefficients and reactants are also raised to their coefficients. And in this case, our reactant is a solid. This is why it's a solubility product. We are going to look at a equilibrium product between Ca2 plus and F minus, where we square the fluoride because of its stoichiometry. So performing a substitution, we have said that the concentration of calcium is equal to S, and that the concentration of fluoride is equal to 2S, and that has to then be squared. So this expression becomes S times 2S squared, or 4 times S squared, or S cubed. That is equal to KSP, which is our 3.9 times 10 to the negative 11. So then if I want to solve for S, that is going to be 3.9 times 10 to the negative 11 divided by 4. All of this raised to the 1/3 power, or take the cubed root of. So let's see actually what this is. So let's see here, 3.9 times 10 to the negative 11. Divide that by 4 and raise to the 1/3 power. I get 2.136 times 10 to the negative 4. And remember the unit of molar solubility. This tells us the number of moles of calcium fluoride solid that are dissolvable per liter of solution. So this is the molar solubility. This is our max number of solid moles dissolvable. Looking at this quantity, right? Pretty small amount of moles dissolvable, but that makes sense when you think about the value of K. K is very, very small. So this equilibrium does not have a large value, meaning there should not be large quantities of ions in my saturated solution. I'm not going to dissolve that much. Now, up next in part D of this question, we are going to be asked to do something that kind of like makes this realistic, because like I had somebody ask this the other day, like, why do we care about any of this? So we care about solubility and solubility equilibrium because of the phenomena of like precipitation, right? What can I do to force some things to dissolve and some things to not dissolve or be soluble in water? And if we are like observing things like kidney stones, which are innately a precipitation reaction, or using like barium salts for imaging in medicine, which requires us to think about, well, how much barium can we put in this person to make it effectively dissolved or not? We are probably not going to be measuring out in the lab like mole quantities, but rather mass quantities of that salt. So I've asked in this question what the solubility of the substance is. This is like our realistic max, which says this is the max number of grams solid dissolvable per 1 liter. And we use solubility often instead of molar solubility, because again, like if you're trying to prepare, let's say, a saturated solution, or if you're trying to figure out like how much of this barium can I give to this person so that they actually have like barium dissolved in their system, you got to think about like how many grams you can administer in that particular dose. So let's think about what we know. We know that the max number of moles is 2.136 times 10 to the negative 4 moles of calcium fluoride dissolvable per liter. And I want to do something to this unit so that I'm left with grams of calcium fluoride per liter. This means that I am looking for a conversion that allows me to get rid of the mole unit and replace it with a gram unit. So thinking just about moles and replacing it with grams, what do I know that relates grams and moles? That's molar mass. So if I take my molar solubility and multiply by my molar mass here, which is approximately 70-ish grams, then I get 0.01495 grams of calcium fluoride per liter. If you use like the non-approximate molar mass, I think you get around with rounding 16 milligrams, which is what I'm going to do here. This is like approximately 15 milligrams of calcium fluoride per liter. And again, like, is this something that's rational? Yeah, I think this is something that we can make sense of because we know that KSP is small. So at equilibrium or at our saturation point, the number of ions in solution is small. And this working backwards means that the number of solid particles dissolved is small. In other words, I have a very low solubility. So in our next lecture video series, we are going to take this understanding of KSP and molar solubility and work with it to actually like look at the things that we care about, right? These precipitation reactions. Because from Gen Chem 1, we have a really limited idea of what precipitation is, right? We looked at our solubility rules that we now know don't really exist, right? Because what do we talk about when we say something's like sparingly soluble or partially soluble? We're talking about this idea of like partial dissociation. We're talking about the solubility equilibrium. So let's inject our understanding of precipitation reactions with this newfound knowledge about what is actually happening when we dissolve an ionic salt in water to create a saturated solution, aka when we're in a dissociation equilibrium. So that's coming up next, dissociation equilibria and precipitation reactions.